The intertertiary structure, there are 3 common folds. Again, maybe pictorially be able to pick them out. If I cut and paste from the handout, we'll be able to interpret what was that a roster fold, is that a tin barrel, is that a beta barrel. It's the kind of stuff you just need to be able to pick up on. Know your interactions, which amino acids are involved in those interactions. Hydrophobics, hydrophilics, salt bridges, hydrogen bonding, disulfide bonds. Hydrophilic and hydrogen bonding are pretty much the same grouping of amino acids, suppose. Then we talked about denaturation and aggregation.
Can you repeat that? The hydrophobic.
What's that?
Each one is similar to the
Hydrophilic and hydrogen bonding are basically the same group of amino acids. You know, it's similar interaction. I want to update this. This is kind of, it must be, yeah, this is an old, take this, let me re-outline this part, because I redid this at one point for the notes to make it clearer. So for denaturation, there are basically 3 methods. There's molecular motion. Under that we can have temperature and mechanical strains. There's pH, and there's polarity, under which we have solvents, detergents, and chaetropes. So I wanted to just reorganize this right here. Mechanical and temperature kind of go together. Go into molecular motion. pH is its own little collection, and polarity is another group of subcategories of solids, detergents, and chaetropes. So, and know which interactions are affected in each. Now, in molecular motion, it's everything. It's just a gross, just ruining of the structure. pH, of course, affects things like salt bridges and hydrogen bonding, because you're changing the protonation state. And polarity, you're affecting the hydrophobic effect. So the hydrophobic interactions are what are being interrupted. All right, everybody follow with denaturation? All right. Next, we talked about X-ray crystallography versus NMR spectroscopy. I don't expect you to be able to really give me an in-depth explanation of each of these. They're both kind of complicated. I gave a very shallow kind of description of each. Understand some basic principles, some of the limitations of each. That big chart that I gave at the end, that's kind of the take-home points I want people to learn. You know, the pros, the cons, the limitations, basically some of the equipment needed too. So that's kind of what I'm trying to get at. You know, let's compare the 2 methods, what's good and what's bad about each one. All right, so look at that. That table is what to focus on. Okay, quaternary structure. Obviously, we talked about this. This is basically multiple proteins binding together in a larger structure. Hemoglobin is a major example of this, but also the structural proteins are prime examples because we have extended quaternary structures of things like keratin and collagen. All right, moving to structure and function. I went through the 3 categories. The structural proteins, for the 2 examples given, know their amino acid composition. Yes.
You know, for keratin, 70% non-polar and 30%.
So 70% polar, 30% non-polar.
Do we know the amino acids associated with them, or should we just write?
No, I just know the polar, non-polar. Yeah, don't worry about exactly which amino acids fall into which. Now, that's a good point to mention. I want to go back to interactions. This is an area where you're going to have to know your amino acids again, not in terms of structure or code, but do know which categories they fall into. So methionine is non-polar, histidine is charged. So For this, remember your amino acid categories. Which amino acids fall into which category? Okay? So this is the one carryover from exam 1 into exam 2. Yes? We're going to get to that. That's enzyme stuff. Well, if you know the charged amino acids, I'm not going to go too much on acid base. I'm not going to go too much to which amino acid counts as a general acid or base. I'm not too concerned about that. They are considered general acids and bases, so you only have to know them as, as a base, as something as a base or an acid equivalent. You don't need to know which amino acids fall into that. I'm not gonna make you memorize all that list. Okay? Okay, so I just wanted to bring that up because I will bring those amino acids back for interactions. So know your amino acid categories. Names and categories. Structural proteins. Composition. Again, 70%, the 70-30 that we saw in keratin, but also in collagen we have the proline, the glycine, and the other amino acids. Structurally, what basically secondary structure. We're talking alpha helical versus left-hand helix. What their function is in the body: hair, nails, connective tissue, and the actual chemical cross-linking, whether that's disulfide bonds or hydroxylysines as the cross-linkers. You don't need to know all those extended cross-linkings that I showed in that one slide. That was just examples of how hydroxylysine could be used to make cross-links, the actual chemical connection. Yeah.
This question the amino acid, the sulfate, if you're going to form a sulfate, it would be with negative amino acid like E or T.
Yeah, aspartic acid. Yeah, aspartic acid, glutamic acid. Those can form salt breakers, as can histidine, lysine, and arginine. Okay? Those are positive. You need a positive and a negative positive. So you need one of each, right? Yeah, but either one could be involved in a. I could say each amino acid in all the salt bridge, and obviously the one that's one of the charged amino acids would count as that. H-R. And you don't even remember all the one-letter codes for all that either. Just know the names in their categories. I'm not going to retest people on the codes. Okay? All right. Anything else before I move forward? Go further. So we trudge further forward into this stuff. Keratin, collagen, and don't forget the importance of vitamin C in collagen strength that is used to create hydroxyproline and hydroxylysine, both important for its strength and construction. Okay, membrane proteins. There were 3 groups. The integral, which actually sit in the membrane, and they have a hydrophobic exterior of the amino acid sequence that touches the hydrophobic portion. The anchored are typically globular proteins that are anchored by some sort of lipid. You have the 4 anchors here. Know the amino acid and location that those anchors occur. So acetylmethylation is a cysteine somewhere in the structure. And myristylization is a N-terminal glycine. Isoprenylation, C-terminal cysteine. And GPI is simply the C-terminus of the protein. Okay? Know basically what the lipid is and know how they're linked to the protein. All right? Those are 2 things you need to know about the anchors.
For G-trans, is the C-terminus of the protein?
Yes. So, and it doesn't usually have, I don't believe it usually has a specific identity on that one. It doesn't have to be a cysteine or a lysine or anything. I believe it's just the C-terminus. Peripheral proteins are simply associated to the surface interactions, usually charged on the surface of the membrane. So whether it's a charge interaction, positive, negative. And peripherals tend to dissociate very freely back and forth from the membrane, because that's their job. Now, Those are the three. Glycosylation is an additional feature of most of the membrane proteins. Because membrane proteins sit on these membrane structures, which can be vesicles, the external plasma membrane to a cell, they need to often have some sort of label or tag. The protein is the best place to put these tags, and these tags on things like glycosylation. O-link attaches to threonine and serine, and N-link attaches to asparagine. All right, and they're simply tags on the surface of membrane proteins. All right, pretty good on that. Moving forward, with the globular proteins, the binding proteins were the first. We talked about myoglobin and its binding curve, know how to read, interpret, possibly even sketch, the components of a myoglobin binding curve. Very simple though, it's simply pressure of oxygen, fractional binding. It curves up to an asymptote of 1, and at 1/2 is where we find, in this case, the P50. Well, if I was doing it in concentration units, I'd call it the kV. That's a myoglobin binding curve. That's what you need to know about that particular portion. All right? You know something about heme a little bit. So obviously heme is important. The different oxidation states of heme, that should be on there too. And just the basic function of heme is that it binds oxygen. Now moving to hemoglobin. Hemoglobin has the tetrameric or quaternary structure, and the whole point of that is it is cooperative. So when you see that sigmoidal curve, you know cooperativity exists. You don't have to be able to sketch the sigmoidal. You don't have to be able to interpret the sigmoidal. You have to know a sigmoidal curve is a hallmark of cooperativity. The T versus R theory is very important, so understanding that T is the weak binder and R is the strong, and that different situations influence the change from T to R or R to T, resulting in a change in the binding capacity or the binding ability of hemoglobin. So, just within the tetrameric state itself, one T to R transition pulls the others into R, forcing the hemoglobin to suck up oxygen very quickly. And then another transition of one of those back to the T, forcing them all back into T, forcing the entire hemoglobin to dump its oxygen. So that's the cooperativity, this interaction between the different subunits, causing them to be either highly tightly binding or very weakly binding. And of course, your allosteric modifiers, such as pH, which is the Bohr effect, carbon dioxide, and BPG, will force this R to T transition because they're influencing and causing hemoglobin to dump its oxygen. Remember those equilibria I drew on the board. I might ask you to reproduce them and perhaps even explain them. This might be the only portion of the exam that gets anywhere close to a long answer question. Usually like 2 sentences. I don't like long answer questions because I don't like to read too much, but I do want people to be able to express themselves. So you write the equilibrium and then you explain what's going on. Oh, well, the pH is lowered, the H plus binds, pushes the R to the T, oxygen is released.
Can you go to the BPG, explaining that?
So what happens in BPG, first what I would do, let me demonstrate. If I were to ask you about BPG on the exam, first I'm going to draw the equilibrium. I'm going to draw all the O2s in. So how I would explain this is that BPG binds to the tetramer of hemoglobin, forcing all of the hemoglobin subunits into the T state. This conversion then causes these hemoglobins to release all 4 oxygens. So that's the kind of thing I'm looking for. Write me the equilibrium and briefly explain it. It took me about 2 sentences to explain it. I don't want essays. You don't have to write an essay. Please, for the love of God, no. We don't like essays. I remember Dr. Bamani, who used to teach here, he gave the mistake of giving an essay response on one of his exams in the molecular. Never. they're hard to grade because then you're like, well, that's wrong, but they're kind of, but they missed this because it hurts my head. So, especially when you're working with like 40 to 60 exams, like, I don't know. So, I'm not going to look for long answers. Again, a couple sentences explaining it. I'll look it over again as long as I can see the equilibrium and a legitimate explanation about what's happening in that equilibrium. And don't give me a physiological. People try to do that. Well, oxygen binds at the lungs, and that's necessary to carry to the tissue. That's not explaining the equilibrium. I want to see, in a chemical, very micro sense, what is going on in this reaction, how this is working. Okay? So draw it and explain. Yeah.
That was something that happened during pregnancy also.
Well, so this transition is this kind of modifier, this allosteric modifier, helps out with things such as high altitude adjustment. It also helps out, it also is part of the fetal maternal interface, because it helps push the oxygen from the mother into the fetus. Yeah, well, the fetus binds the oxygen, yes. And since the fetus is non-responsive to BPG, it's the total trend is that the oxygen is going to push in one direction, mother to fetus.
When we actually take something like that and trade that before that.
No. Simple as this. What? It's as simple as this. I like to keep it simple. I like to tell you what I want to see, and then you're going to show that to me. I don't want to, I'm not one of these guys who are tricky like, oh, well, now you need to go with extra self-interpretation. I don't want to do that. That's unfair to you, and that's painful to me. Keep it simple. Let somebody else, let the MCATs mess you up that way. Interpret this graph and explain. That's their job to hurt your heads. I'm just trying to get you through this. All right, I'm going to ask a quick multiple choice question on sickle cell anemia, how it relates to malaria, how it relates to the whole R to T transition, and the simple modification that leads to aggregation. Okay, but maybe something quick and simple on that. Don't expect too much on malaria, on sickle cell anemia. Okay, everybody comfy so far? Moving forward to enzymes, the big portion here. Know your categories. As I mentioned, I'm going to give you a reaction. I'm just going to put it up there and say, which category does this reaction fall in? And you have to be able to determine which of the 6 categories that reaction is. Is it transfer? Is it a hydrolysis? Is it a lyase reaction? Is it a transfer, a ligase reaction? Okay? So look for the hallmarks of each of those categories, and then you can figure out which one it falls into. And of course, there'll probably be multiple choice, so I'm going to put the one that tricks you too. Oh, that's a hydrolase reaction. I'll write down hydrolase. And it won't be a hydrolase reaction, but you'll think it is, and that's your wrong answer right there. So that's how multiple choice can be meaner than short answer. Because at least short answer, you got, oh, I can fudge something here. Multiple choice, you'll be cool. You go, ooh, that's my right answer. No. So that's how multiple choice is meaningful. Went through a little bit about the definition of catalysis. We don't want to go too much into that. Michaelis mentioned the graphs, again, are important. Getting your Vmax, getting your Km, converting between Michaelis and livelihood of birth. I have yet to decide which one I'm going to do. I'll probably decide tonight or tomorrow night when I finish writing the exam. I'll choose I'll do this one this time. And I'll do the opposite one on the final, but, so, prepare for both. Because I don't even know which one you're going to get.
Can you give a quick example of one?
Sure. Which one are you most uncomfortable with? Reading a line with a verb or drawing a line with a verb, or the other way around?
No,
So making it?
Yeah.
Okay, so if I gave you this, and I said, so that's your green, that's your substrate. If I said this was 50, so you agree that. So we know our Vmax is an easy one, right? Vmax is 50. That's your asymptote. And I'm going to make it very obvious on the exam. Now, how do I get to the Km? The half, which is 25. But 25 is not my Km. People do that all the time. There's 25, no, 25 is not the Km. Read down to the x-axis, and you'll say that's 10. And I only said it was 10 because that's what you would read on. You're going to get like a perfect graph on the exam. You can read it beautiful. So you'll have no problem finding the Vmax and Km. So if my Km is 10, and my Vmax is 50, and then I'm going to ask you to write those all out for me. You're gonna jot down Vmax and Km, and then you need to plot them on the line we revert. So the Vmax, the x-intercept is 1 over Vmax, which is 50, which is 0.02. At the y-intercept, the x-intercept is negative 1 over Km, which is negative 1 over 10, negative 0.1. So that's where that one should go. And so this will be like, say, 0.02, 0.01. This is negative 0.1, negative 0.05. You'll have all the scales. You just have to figure out where to plot your points. And draw a line. 2 points to find a line. In this case, it's these 2 points in a straight line. When you do this, if you were going back, your 2 points will be your asymptote and this little intercept. So when I look for the Michaelis-Menten point, I'm going to look for the asymptote, and I'm going to look that you put your intercept, your little Km point there. That's what I look for when I see that correct. If I don't see those right, they're in the wrong spots, that's when you start losing points. So be able to calculate, read, and you'll read the graph, figure out where to put it, where to read it, what the value is. It's all about graph reading. Better? Okay. Now, and don't forget, in addition to competitive and non-competitive, we have changes in Vmax and Km. And understand what's going on there. So, competitive is a change in Km, a raised Km, because the inhibitor binds at the same active site as the substrate. Vmax stays the same. In non-competitive, the Vmax drops because the inhibitor is binding at another site, a non-competitive or allosteric site, brings down the amount of enzyme, Km stays exactly the same. So lower Vmax, same Km. All right? Be able to read those on the graphs and interpret which one's which. Yeah? Yes. It's a non-programmable calculator. All you gotta do is 1 over stuff. Easy as it. All you gotta do. And like I said, I'm probably gonna graph it with all the points on there to make it a nice visible graph. You don't need to sit there and convert every point. I've seen people do that. So they'll have, let's say I gave them a graph, you know, in Excel, make my nice little graph with all the squares. I've seen people read each of these points and then try to do an inversion and try to graph them. No, don't kill yourself. It's going to take you a good 30 minutes to do that. 2 points, Vmax Km, defines one to the other. That's all you need. All right, mechanisms. Oh, we're running out of time here. Okay. 4 mechanisms. Again, I could ask you to recite these and briefly define what they are. Or I could just ask a quick multiple choice question. We'll see how I feel. Transition state stabilization is the locking key, is that induced pit model where the enzyme and the substrate modify. The enzyme is binding, remember, the transition state, not the substrate. General acid-base catalysis, that's your draw A mechanism. Will be the only mechanism drawing you'll have to do for this entire semester. If you can at least draw me where the base is supposed to go and where the acid is supposed to go, that's partial credit right there. You have to be able to draw, so where are you going to pull off an H, where are you going to put on an H, that'll tell you where your acid and base is supposed to go. Well, no, what I'll give you is I'll give you
Products and-
the product that, the substrate and the product. You have to tell me how you get there, okay? So you'll have to say, oh, I need a base here, an acid here, and then, and that's how it gets here, okay? And then show you the result. You can fill covalent intermediates, where we talked about burst kinetics, we talked about the ping pong pattern, you might need to reproduce that, that was a big hint. The ping pong pattern, don't forget, I went over it twice. So, yes,
And look at the arrows, and you have to give
Yes.
the-
I will give the arrows with blank spaces, and then you have to fill everything in where it goes. Okay? Coenzymes, cofactors, I got a few facts on those, multiple choice kind of questions. The zymogen. The zymogen, my favorite thing to do about zymogen is ask people to spell zymogen, or to write it. And I get the funniest thing. I get zygomes, no. Zymogase, no. You have to, it's a zymogen, okay? Yeah.
Sounds weird, that's some waste. Yeah.